All right, guys, quick video today. We're going to just talk a little bit more about calculations on the normal curve, right? So yesterday or not yesterday, last lesson on the calculator, we saw how to do norm CDF, right? To get percentages or areas underneath the calculator. So today we're going to just do one more other thing on the calculator. Again, pretty short lesson. So if you want, pause the video. Right, and try this warm up. It's going to be these first three questions. All right. So for this first one, we're comparing the weights of a great white shark with that of a Great Dane, and we want to know how much does the dog have to weigh to be in the same percentile as the shark. Right. So when we say same percentile, right, we're in essence saying, well, maybe their normal curves look different. Maybe this is for sharks, right? And this is for dogs. Maybe dogs have a lower standard deviation, right? Doesn't really matter. Because that shark, well, we can find its percentile rank by finding its z-score, right? And we can get that, and let's say, I don't know, I'm just making this up, but let's say that was 80%, then we can say, right, the shark is heavier than 80% of all other sharks. So on the corresponding normal distribution for dogs, we will want that to also be 80%. And so these would be 80% at the same z-score, right? So in essence, we just want to know how many standard deviations that great white shark is above other great whites, and same thing for the Great Dane. So the calculation for the great white should look something like this, right? Like that, right? So the shark, he weighed 2,700 pounds, right? Minus the mean over the standard deviation gives a z-score of 2.4375. So the shark is 2.4 standard deviations above the mean. So he's an extremely large shark. So we just do the same thing for the dog. If we want it to be the same percentile, right, it should have the same z-score. So I can solve for x, which would be the weight of this dog. All right, for this next one, Peter is analyzing a data distribution and types in that. In a complete sentence, explain what this means. So when he typed this in, he got this answer. So as a percentage, that's going to be 57.6% approximately, right? So that means about 57.6% of the data is, well, let's look at this data, right? This is our lower bound. This is our upper bound. And because this is a 0 and 1, right, I know they are using z-scores, right? They're using this picture where that's 0, 1, 2 standard deviations above, -1, -2. Right, so this is going from -1.2 to 0.5. So it's looking at this area. And it's saying that area is 0.576393. Right, so we can say 57.6% of the data is between -1.2 standard deviations below the population mean and 0.5 standard deviations above the mean. Right, Quinn is analyzing his class's test grades out of 100 and types in this. In a complete sentence, explain what this means. So his normal CDF is going from, so lower bound of -1,000 to upper bound of 65. Well, this is not using z-scores because I see, right, the population mean here is at 82, and the standard deviation is a 12. So the average grade on this test was 82 with a standard deviation of 12. And students that scored between -1,000 to 65 was about 7.8%. So 7.8% of the class scored 65 or lower. Right? In other words, 7.8% of the class failed. Well, actually, I guess scoring a 65 is not failing. So 7.8% of the class scored 65 or lower on a test with a mean of 82 and a standard deviation of 12. Right, and it makes sense to use the population, right? It makes sense that these are population means and population standard deviations, because if he's analyzing all of the test grades out of the entire class, well, that is the entire population. All right, so we're going to do a really quick question. We're going to review what we did yesterday with the norm CDF, A and B, right? And then we'll see if we can answer letter C. So draw a normal curve for each and shade your appropriate region under the normal curve. Graph the inputs for the norm CDF function for each. The amount of soda in a standard can is normally distributed with a mean of 12 ounces and a standard deviation of 0.6 ounces. So if I draw a quick pic, it's going to look something like this. Mean of 12. Here is one standard deviation. Here is 2. Here is one standard deviation below 11.4. Two standard deviations below 10.8. So a soda can is considered unsellable if it has less than 10.5 ounces. So less than 10.5 ounces. It's going to be right there. So if 250, I think I'm going to change this to 2,500. It's going to be, I think I got to change it to a bigger number. But if that many soda cans were pulled by a company to check the volume, how many would be expected to be unsellable? So let's get the percentage that are going to be less than 10.5 ounces. So to do that, we can use z-scores again. But to keep it simple, I'm just going to use the actual values. So I'm just using -1,000, right? Because if our standard deviation is 0.6, -1,000 is many, 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 many standard deviations below the mean, and all we need is like 5 or more, we said, right? So -1,000 is fine, to 10.5, and mean of 12, standard deviation of 0.6, right? You type that in your calculator, and you are going to get 0.00621. That's rounding, right? It's 0.0062096 something, something, something. So approximately this, right? So yeah, let's change this to 2,500 soda cans. It'll be 2,500 on your notes. So how many would be expected to be unsellable? Well, that is around 0.621%, so less than 1%, right? That's actually probably pretty high, right? If you were a factory, you would want probably like as minimal as you can soda cans unsellable. So anyway, to find the number, we would just take 0.621% of 2,500. So let's multiply this by 0.00621. And let's see what that gets us. Right, I'm getting around 15.5 cans. So around 15.5 cans would be unsellable. If you want to round up to 16, that's fine. But around 15.5 cans. All right, so a soda can is considered to be overfilled if it has more than 14 ounces. So same diagram, except instead of a lower bound this time, right? If it's overfilled, we have an upper bound. So 14. How many of, again, let's do 2,500 of the soda cans would be expected to be overfilled? So I think this is going to be even less because it's even more standard deviations away than 10.5, right? Because this is going to be 13.8 is going to be there. So it's going to be more than 3 standard deviations. So it's going to be even less soda cans, I can tell already. So in this case, I'm looking for that area above. So my lower bound will be 14, and my upper bound will be 1,000. And give me a sec, let's see what this is. I'm getting around 0.000429. So as a percentage, that is approximately 0.0429%. All right, that's less than 0.1%. That's less than 1/10 of a percent. All right, so it's a really, really, really minuscule amount, which should be good. You don't want any cans to be overfilled. All right, that's kind of dangerous. All right, so you can see as you get to big standard deviations, you can see how little of the population really is, right, in those standard deviations. So if I multiply this by 2,500, I am getting approximately 1.07 cans. So about 1 can out of every 2,500 soda cans, right, would be expected to be overfilled. All right, now it asks, what weight would a can at the 60th percentile have? All right, so the 60th percentile. Well, I know the 50th percentile is right down the middle. That's the median, right? Because here's 50% of our data, right? When you are at a percentile, right, you're said to be above that percent of the population. So that a can at the 60th percentile would weigh more than 60% of all the other cans. Right? I know within 1 standard deviation, that's 68%, right? Within 1 standard deviation of the mean. So here is going to be 34%, right? So this piece right here, that is the 84th percentile, right? 1 standard deviation above the mean, that's already the 84th percentile. That's actually really high already, right? So I got that, right? 50% plus 34%. This is the 50th percentile, of course. And so we're looking for the 60th percentile. It's going to be somewhere in between 12 and 12.6, right? So you can't just do like a linear interpolation, right? Because it's obviously not going to be linear, but we know it's somewhere over there. That there is around the 60th percentile. So somewhere between 12 and 12.6 ounces is what we're expecting for the weight of the can. So to do this, we can't do norm CDF. We have to use another function in our calculator, all right? So let me switch my screens over to the calculator and we can talk about how to do this. All right, let me get my slider. All right, let's go to a new calculating page. All right, so we're gonna go to menu. All right, probability and distributions, just like before. All right, but instead of norm CDF, we're going to be doing inverse normal. All right, so norm CDF, that allowed us to find the area underneath the curve, right, the percentage. But in this example, we already know the percentage, right? We know it's the 60th percentile. We already know the area under the curve is going to be 0.6, right? This can is way more than 60% of the population. So we go to inverse normal, right? It's kind of like the inverse function we're doing here. So we're doing inverse normal. We're going to type in the area, which will be 0.6 or 0.60 if you want 60%. Again, we could have standardized it and found it, found the z-score, right? Well, let's just type in the data this time. The mean was 12. Standard deviation was 0.6. And hopefully, we're going to get the answer we expect. That is somewhere in between 12 and 12.6. And there it is. The can would weigh 12.152 approximately ounces. All right. So that is the inverse normal function. Kind of just the opposite of norm CDF that we were doing in the last one. All right. So let's resume share here. So for this one, we would have typed in inverse norm 0.6, 12, 0.6. and that was equal to 12.152, approximately. So a can that weighs 12.152 ounces would weigh more than 60% of the other cans. All right, I said we could have done this with z-scores. I just want to show you that real quick. All right, so if we're doing this with z-scores, we're typing inverse normal, 0.6, comma, 0, comma, 1, right? And this would give us the z-score of the can. And so to get the actual weight then, well, it's kind of silly. Like, you wouldn't want to do this, but let me go to, all right, I'm just going to do it on the calculator. I'm sure you guys will believe me once I do this. All right, by doing this on the calculator, I type in 0 here and 1, I'll get, wait, that's weird. Hold on. All right, yeah, so when I did this, I got approximately 0.253347 something. All right, so what this is saying is the can 60th percentile would be 0.25 standard deviations above the mean approximately, right? So I don't know why you would ever do this, but if you did it this way, right, it's good to have the understanding of what's going on. Right, we could still find the weight of the can by using the z-score formula, right? And we know the z-score, of course, is x minus the mean over the standard deviation. So we can say 0.253347 equals the weight of the can at the 60th percentile minus the mean of 12 over standard deviation of 0.6. And if you solve this, right, you're going to get 12.152 ounces as well. So you wouldn't ever really do it this way, but I just want that concept of z-scores, right, to make sense. So let's practice with these inverse normal calculations. The time spent by a teacher at work in the holidays is normally distributed with a mean of 20 hours and a standard deviation of 5 hours. All right, those are completely made up numbers. Yeah. So what amount of time do the bottom 20% of teachers work? So when we do our inverse normal, right, 20%, well, we know the area, right? We're trying to find the number of hours here. So that's why it's an inverse normal function. So we're going to do inverse norm of, so the area is going to be 0.2, comma, mean of 20, and a standard deviation of 5. And again, all we do is type this into the calculator, 20 and 5. And what I got was, oops, I typed in the wrong number, 0.2. What I got was 15.7919. 15. I should really tell you what to round to, but let's round to the nearest tenth. So about 15.8 hours. So the bottom 20% of teachers work 15.8 hours or less. Right? So here is where it gets a little interesting. What amount of time do the top 20% of teachers work? Well, you want this area, the top 20%. And right, this area here is 20%, just like this area here was 20%. But in my inverse normal function, right, this area, well, that is the left bounded area. That means that area always goes from the left, right, to the right. It's always bounded by that area. So how could I get the top 20% when this area is always left bounded, right? It wouldn't make sense to type in the same thing because I'm going to get the same answer, 15.8 hours. And obviously, the top 20% of teachers don't work 15.8 hours. It's the bottom 20%. So what could we do? So just a heads up, in this inverse normal calculation, this is the mean, that's the standard deviation. And here, this is the left bounded, right, area, or probability, or percentage, right? So what we could do is, well, if we're looking for the top 20%, well, couldn't I figure out the bottom 80%, right? Because figuring out the bottom 80%, oh, that's going to give me the same number right there. So to get the top 20%, I would type inverse normal of 0.8, comma 20, comma 5. And let's see what this gets us. 0.8, that is approximately 24.2 hours. So the top 20% of teachers work 24.2 hours or more. And this last one here, this is where it gets really interesting. What amount of time do the middle 40% of teachers work? So we want an interval for the middle 40%. All right, so I like this question. This one requires a bit of thinking. So the middle 40%. So I know the very middle, that is the mean, right? So if I'm looking for the middle 40%, well, that means 20% of my data is on this side. And 20% of my data is going to be here, right? And we know 20% of the data, that's less than 1 standard deviation, right? Because 1 standard deviation, again, that should be 34 and 34, because within 1 standard deviation of the mean, that is 68%. So it's just really good to have those general numbers to see if your answer makes sense or not. So there's the middle 40%. If we know the entire area is 100%, well, that leaves 60% of the area over there and over there. So that means here is 30% of our data, and here is another 30% of our data. And altogether, that's 100% of our data. So if we want the middle 40% of teachers, well, we got to do a combination of what we did in A and B, right? Again, we're doing left bounded areas. So what we would do first is get the 30th percentile, right? By doing an inverse normal with this 30%. And to get this upper bound here, we would do an inverse normal with 30 plus 20 plus 20, which is with 70%. So we need to do 2 inverse normal calculations to get that middle 40% here. So this would be an inverse norm of 0.3, comma 20, comma 5. And to get the upper bound, inverse norm of, well, that's 30, 50, that's the 70th percentile. So do an inverse norm of 0.7, comma 20, comma 5. Right, so I'm going to do that real quick just to get the answer for you guys. 0.3. Obviously, you guys should be doing this yourself as well and checking it out, make sure it makes sense. But that's going to be in between 17.4 and about 22.6 hours. So in between 17.4 and 22.6 hours. All right, and probably just write it as an interval. That's the nicest, quickest, easiest way. Cool. All right, and lastly, I'm just going to make a logic check. So the standard deviation was 5 hours, right? We know it's less than 1 standard deviation, so it is less than 15 to 25, right? So perfect, makes sense. So 2 more questions down here on the bottom. You guys can try these on your own. I will post up an answer key with this, with the notes. And actually, I'm just going to pause the video now. I'm going to do these 2 problems. Unpause it. You can check it. So go ahead and try 2 and 3. And I'm back. All right, that's what I got for the last 2. Double checking my work. Let me know if I did something wrong, but I'm getting 517 grams for the top 4% and that interval for the middle 50% of free fall time for these jumpers. All right. So as always, if you have any questions, let me know. Oh, I forgot to mention at the start of this video, we are heading into the home stretch of things. Only a couple more lessons left. So on Monday, we are going to be having a quiz. All right, don't worry, this quiz is a freebie quiz. So the way this quiz is going to work is it's going to be optional. So this is an optional quiz. You don't have to take it. But this quiz can only benefit your grade. So if you do poorly on this quiz, it's not going to hurt your grade. And so if you didn't do too well so far this quarter and you want to bring up your grade, you should take this quiz seriously. Otherwise, you should still take it seriously, but just know that it won't harm your grade. All right, so that's going to be on Monday and probably do Wednesday. So take care, guys. We're almost there. Enjoy the time left we have together. I'll see you guys soon. See ya.